Hi everyone, this is CS61B Spring 2020 Midterm 1. My name is Soham and I'm going to be walking through question 3 part A. Consider the following function, which is intended to carry out one step in a not terribly efficient sorting procedure. Okay, let's see what this function is. The function is called swap up. It takes in an array A and it iterates from I equals 0 up to the length minus 1, not including that. And at each I, it looks at the element, right? It looks at the ith element in A, and it compares it to the ith plus 1 element in A. If the ith element in A is greater than the I plus 1th element in A, we perform a swap. Right? That's what's happening right here. Is some sort of swap. Okay. Let's try to understand this function a bit better by walking through some example. So let's say that we have some array A, right? And let's say it contains the elements 2020. Okay? So let's walk through what will happen when we call a function swap up on A. Okay? So let's say that this is going to be our final answer over here. Our final answer. Okay? This function actually just is going to modify A, but in order to understand like where we come from and where we go to, I kind of want to show 2020 and the new end result. But note that this is a destructive process right here. Okay. So for our final answer, what we're going to be doing is we first compare 2 and 0 together, right? 2 is greater than 0, so we perform a swap. 0 moves to the front, 2 moves to the second spot, and then 2 and 0 is still there, right? Now I goes to 1, we compare 2 and 2, right? 2 is not greater than 2, so there's no swap. Then we compare 2 and 0 together, and we see that 2 is greater than 0, so we perform another swap, and we get our final answer being the array 0202. Okay? This is the gist of how swap up works. So let's see what question 3 part A is asking us. It's asking us to fill in the method swap up list so that it non-destructively returns the list resulting from applying the same algorithm as swap up, but with the input sequence being an int list rather than an array, right? And we see here non-destructively. I want to emphasize what non-destructively means. Non-destructively means that we're given some linked list L, right? Let's just use the same example, right? 2, 0, 2, 0. After we execute this function call to swap up list, this linked list L that we were given should not have changed at all. Non-destructively means we're creating a new linked list and we're not changing L. Not changing means not changing the values of the heads and not changing the pointers, right? So we want a non-destructive implementation, which means we're creating a new linked list, right? Okay. And I think the next step is to look at the skeleton code that's provided. So we can kind of see where we can go from here, right? The skeleton code that's provided indicates a recursive structure. And if that's a big jump, I'll try to explain why my intuition told me this, right? Looking at the skeleton code, we see it's broken up into 3 main sections, right? An if, else if, and else. The if just returns L automatically, right? In other words, this is a base case. And here, else if is a recursive call, right? Let's put recursive call 1, RC1, and then the second one is the recursive call 2, right? So this is the breakdown of the skeleton code that's provided, right? And before I start trying to put in code in the skeleton, let's take a step back and see what we want our function to output, right? Whenever I like to code linked list problems, I like to see what the input is and what we want our function to output. So our input is L here, right? And our output is the same as the array, but in a linked list form. So our output, we'll say output, is going to be 0, followed by 2, followed by 0, followed by 2. Okay, this is what our output is. This is what our output we want. So in order to execute this, let's start with the base case, right? Base case is something we can like check off, and then we'll move on to something a bit tougher, i.e. the recursive calls. So in the base case, what's the simplest instance of this problem? The simplest instance of this problem is when L is either null, right? Or are there any other times we'd want to return L immediately? Let's think. If L is one element, right, if it's one link, it doesn't have any links to compare it to, right? If it's a one element link, we know we're just going to return L immediately since there's nobody we could potentially swap it with. So if L is null, I messed the double equals. If L is null, or L dot tail is null, we return L, right? Because there's no swapping that can be done, and we know L is already in its swap up listed form. Okay, now we're done with the base case. Let's move on to the recursive calls. So we see here there's two recursive calls. So the first recursive call must be if we execute one choice, and the second recursive call must be if we execute another choice, right? So we have two recursive calls, right? And since there's two calls, there must be two different choices that we're making. So let's try to think about these choices. Choice 1. We can look at swap up and see what the choices are. So choice 1 is if A of I is greater than A of I plus 1, right? If the current is greater than the next. Right? That's the first choice. In which case, we swap adjacent elements, right? And then the second choice, let's put that choice 2, is the opposite of this, right? When the current is less than or equal to, that's a terrible less than sign. If the current is less than or equal to next, we have no swap, right? These are the two choices. But it's a bit more complicated in a linked list format, right? In an array, we just do a swap and then we can keep iterating. But in a linked list, especially when we're creating a new linked list, it's a bit more complicated. So let's try to figure out how we're going to deal with these two choices. Let's think about the first choice. Let's move L down here. That's what I want to do. Perfect. Okay. So the choice 1 is when the current is greater than next, as is the case here. What we want is we want to move the second link, right? This guy, we want to move the second link to be the new first, right? So let's say what we want our recursive call to be. Recursive call is going to move the second element to be the new first, right? And then we want to recurse on the linked list, right? Recursive call on the linked list containing 2, 2, 0, right? We can put in another color just because sure, colors are fun. On the linked list containing 1, right, this link. This is the second link we want, right? And this is the third link we want in our recursive call. So you can put that in here. Right? Okay, this is kind of what we want our recursive call to be. So this is for the choice 1. And it's a bit tough to implement, so let's not worry about it now. We just know that this is the general format. So let's move on to the second choice, when we do no swap, right? For the second choice, move that down there. When no swap is needed, all we do is we move this first link is going to still stay as the first link in our recursive call, right? Actually, it's a little bit confusing here. So this is our return value, right? Return value, that's a bit more explicit. Our return value is going to be, in this choice 2, the link containing 2, followed by the recursive call on the rest, right? Since there's no change. Perfect, we can squeeze that in there, okay? So that's kind of the gist of how our recursive calls are going to work. So now let's try actually implementing this strategy in the skeleton code that's provided. Okay, so looking at the skeleton code, we can see one recursive call is a bit longer than the second recursive call. More specifically, this second recursive call is a bit longer. So we can think about, we could put the longer recursive call there, which is the first one, right? There's more going on in the first situation than the second. So we can put the second recursive call first. This is basically saying if the current is less than or equal to the next, well, what is the current? The current is L dot head. If L dot head is less than or equal to the next, which is L dot tail dot head, right, then there's no swap. So what we do is in our return value, the first link is the link containing 2, i.e. the first element, and the second link is going to be the recursive call on L.tail. So we can put that in here, swap up list on L.tail. Okay, now we can move on to the more complicated choice, when the current is greater than the next, right? In this case, what we want to do is create a new linked list where the first element is the 0 link, and the second element is the recursive call on the first, third, and fourth elements concatenated together of this link, right? Which we can execute by putting in a new linked list whose first element is L.tail, .head, and whose second element is the recursive call, right? The recursive call on, well, the elements, right? These elements, let me get my highlighter to work. These elements aren't connected together, right? So we're going to have to create a new int list in which they're connected, right? Let's create a new int list that goes L.head followed by L.tail. Right? And then we have our solution. So we can kind of quickly run through it once more just to make sure that it works. We have our base case, checking if L is null or L.tail is null, we would just return L. Then we have two choices we make. The first choice, if the current, i.e. the head, is less than or equal to the next, i.e. L.tail.head, we return the new int list containing L.head and the recursive call on L.tail. Similarly, or not similarly, like on the opposite, if L.head is greater than L.tail.head, we create a new int list whose first element is L.tail.head and whose second element is the recursive call on the new int list containing L.head and L.tail. Yes, and I missed one parenthesis. So yes, this is all for question 3, part A.